Welcome to the Cosmic Frontier, where today we're diving deep into the latest discoveries made by the James Webb Space Telescope. The universe is a vast expanse of mysteries, and the James Webb has just peeled back another layer, revealing secrets about ancient galaxies that we never knew. Join us as we embark on a journey through time and space to uncover the tales these ancient galaxies hold. Get ready to be amazed by the groundbreaking findings that are changing our understanding of the universe. The James Webb Space Telescope has once again unveiled extraordinary findings from the farthest reaches of the cosmos. In this video, our primary focus will be on galaxies, some of the most remote ones ever observed, and the remarkable revelations they offer. But before we delve into that, let's take a moment to appreciate these two pivotal images. The first is the renowned Hubble Ultra Deep Field image, an astonishing capture by the Hubble Space Telescope. Once considered the most profound space photograph ever taken, it revealed over 10,000 galaxies by staring into a seemingly empty patch of the night sky, resulting in this stunning long exposure. While other telescopes saw mere darkness, Hubble unveiled a cosmos teeming with galaxies. In a similar vein, the James Webb Space Telescope has performed its own marvels. With significantly shorter exposure times, it has identified thrice as many galaxies as Hubble, without even breaking a sweat. Upon closer inspection, some galaxies exhibit appearances like this one, underscoring the James Webb Space Telescope's unparalleled ability to perceive celestial bodies and features that Hubble could not, thereby broadening our understanding of the universe. From the fringes of the cosmos, recent findings continue to perplex scientists, with one of the latest images, released just days ago, standing out for its uniqueness. This image is remarkable because it demonstrates the various forms of ancient galaxies, revealing the telescope's incredible capability to discern the shapes of galaxies billions of light years away, a feat even Hubble couldn't achieve. The findings, detailed in a recent study, available in the video description, were somewhat unexpected. Researchers noticed that these ancient galaxies appeared significantly more elongated compared to their modern counterparts. In fact, the more we peer back in time, the more elongated these galaxies seem. The study examined galaxies from different epochs, some as young as 600 million years after the Big Bang, and others from a time when the universe was already 6 billion years old. This investigation allowed scientists to categorize these galaxies into four principal shapes: spheroidal, oval, disc-like, and elongated. To put it more colloquially, these shapes could be likened to a volleyball, an oval stone, a frisbee, or a pool noodle. Interestingly, the study also employed more whimsical, food-related terms such as breadsticks and bananas to describe the galaxy's shapes, highlighting the diverse and sometimes amusing ways scientists relate to the cosmos. In the observations of early universe galaxies, a fascinating trend emerged. These galaxies predominantly exhibited either a very flat or elongated form, akin to surfboards or pool noodles. This characteristic was apparent in 50 to 80% of all galaxies observed at these vast distances. Not all, but a significant majority. These galaxies appeared to be flattened in two dimensions. In contrast, galaxies closer to us in time, ones that formed a few billion years later when the universe was much older, tended to be either disc-like or spherical. Notably, spherical galaxies were almost entirely absent in the universe's nascent stages. This shift from oblate, flattened, and Webb much more compact. This early structure of the universe might explain the distinct shapes of ancient galaxies, suggesting a profound connection between the cosmos' large-scale structure and the evolution of galaxy forms. It's believed that the intense forces exerted by the cosmic web in the early universe had a significant impact on the gas within galaxies, stretching them to a greater extent than we observe today. This interaction between the cosmic web and the galaxies, filled with gas and stars during the universe's first billion years, might have altered some galaxies' appearances dramatically compared to contemporary ones. As the cosmic filaments became more dispersed and the universe expanded, the forces acting upon galaxies lessened, allowing them to adopt more spherical forms and reducing further stretching. This theory serves as an initial attempt to explain the observed galactic shapes, but the true mechanics behind these transformations remain a mystery. Nonetheless, this represents an exciting area of discovery in astrophysics. Adding to the excitement is the galaxy Gien's 11, which had been previously discussed as the record holder for the most distant galaxy, observed a title it held until the James Webb Space Telescope began operations. Despite being surpassed in distance by newer discoveries, Gien's 11 remains an object of fascination. It stands as one of the furthest galaxies we've identified to date, showcasing the incredible depth of our universe's history and the ongoing quest to understand its vast expanse. Gien's 11 is situated at a redshift of 11, placing it incredibly early in the universe's timeline about 13.4 billion years ago, or when the universe was just around 430 million years old. Remarkably, despite being nearly 32 billion light-years away, we can still observe it. Though it's relatively small, spanning roughly 4,000 light-years across, about 20 times smaller than the Milky Way, it stands out due to its exceptional luminosity. Its brightness exceeds the Eddington limit by 5 times, the theoretical maximum luminosity a galaxy of its size could sustain without ejecting its gas due to radiation pressure. This galaxy is teeming with young, luminous stars, likely aged between 20 to 30 million years, making Gien's 11 a highly active and youthful galaxy. Recent investigations have revealed at least 9 fainter neighboring galaxies, indicating that the intense star formation occurring within Gien's 11 may be the result of galactic interactions or collisions. Further intrigue surrounds the galaxy's core, which is both highly compact and luminous, suggesting the presence of a massive black hole at its center. Studies have detected signs of black hole accretion, where material is being pulled into the black hole, highlighting the dynamic and complex nature of this distant galaxy. The black hole at the center of Gien's 11 is generating a vast accretion disk, radiating an intense amount of light and energy. According to current estimations, the rate at which this black hole is consuming matter suggests it could lead to the galaxy's demise. The immense galactic winds produced by the black hole are powerful enough to expel all gas from the galaxy, halting star formation entirely. This phenomenon, known as galactic quenching, effectively extinguishes galaxies. For a galaxy considerably smaller than the Milky Way, 25 times smaller, to be precise, this black hole is astoundingly large, with a mass of 6 million solar masses, which is 50% more massive than the Milky Way's central black hole. It generates swift winds exceeding 1,000 kilometers per second, capable of stripping the galaxy of its matter. This remarkable information comes from observations of Gien's 11, a mere speck in the vastness of space. Intriguingly, the same image that reveals Gien's 11 also hints at even more distant objects yet to be explored. These are likely similarly radiant yet diminutive galaxies, rapidly growing with colossal black holes at their cores, presenting us with the next frontier of cosmic mysteries to unravel. The enigma surrounding central black holes in distant galaxies has been highlighted by 2 distinct studies, each uncovering varied phenomena. The first study delved into quasars' immensely luminous central galactic black holes that formed billions of years post-Big Bang, entities that are relatively well understood today. In contrast, the second study concentrated on black holes within much farther galaxies, particularly those that were in their developmental stages and exhibited slightly higher levels of activity without being classified as quasars. This exploration into 21 distant galaxies revealed a fascinating trend. The further back in time we look, the larger the black holes appear in relation to their host galaxies. Specifically, the ratio of black hole mass to galaxy mass increases significantly compared to what we observe in the nearer universe, or in galaxies that are at least 2 to 3 billion years old. Typically, in the local universe, the mass ratio of a central black hole to its galaxy averages around 1,000 to 1. Thus, a black hole with a mass of 1 million solar masses would belong to a galaxy with a total mass of approximately 1 billion solar masses. This standard ratio has been significantly challenged by the findings from these more distant galaxies. In the study of galaxies from slightly earlier epochs, researchers observed a dramatic shift in the mass ratio between central black holes and their host galaxies. Initially, the ratio steeply declined from 100 to 1, then to 10 to 1, and in some cases reached an astonishing 1 to 1. This meant that there were galaxies where the mass of the central black hole was equivalent to the mass of the entire galaxy itself. This finding is profoundly surprising, but critically informative, suggesting that many of these colossal black holes likely originated from what is termed as massive black hole seed formation. This theory posits that black holes initially formed from the abrupt collapse of massive dust clouds, accumulating between 10,000 to 100,000 solar masses in a single event, offering the only plausible explanation for the existence of such massive black holes so early in the universe's history. Contrastingly, the examination of quasars' extremely luminous central black holes presented a different scenario. This investigation into the host galaxies of quasars revealed that the mass ratio between these galaxies and their central quasars closely aligns with the ratios found in more contemporary, local galaxies. This discrepancy is fascinating as it seemingly presents a contradiction, indicating that while some early universe black holes grew to match or even surpass their galaxies in mass, quasars maintained a growth pattern similar to that observed in the local universe, aiding a complex layer to our understanding of cosmic evolution. This suggests that quasars may have a unique growth and evolution process distinct from typical galaxies, or it implies that by the time quasars became active and observable across vast distances, the ratio of black hole mass to galaxy mass might have already reached a state of equilibrium. Interestingly, some quasars are known to have formed as early as 860 million years after the Big Bang. Yet, other galaxies from the same era feature black holes with masses significantly exceeding those of the galaxies themselves, presenting a perplexing conundrum without a clear resolution as of yet. This discrepancy hints that quasars might grow, evolve, and influence their surrounding galaxies in ways that are distinct from other galactic formations. On the other end of the spectrum, researchers have identified the most distant quenched galaxy known to date, a galaxy that has ceased star formation and is likely a precursor to the giant elliptical galaxies that form some of the largest structures in the universe. This galaxy, with a redshift of 2.3, dates back to when the universe was approximately 2.8 billion years old. Despite the challenges in observing such a distant and inactive galaxy, it offers crucial insights into the life cycle of galaxies and the processes that lead to their eventual quenching. Visible to the James Webb Space Telescope, this particular galaxy appears to have been in a state of quiescence for at least 500 million years. However, unlike many early galaxies where black holes are the primary agents halting star formation, the quietude of this galaxy seems to have been caused by external forces. It's likely that neighboring galaxies played a significant role, stripping away its gas through gravitational interactions and leaving it barren of the materials necessary for star production. This presents a different mechanism for the cessation of star formation, highlighting the impact of galactic interactions. This discovery underscores the incredible capability of the James Webb Space Telescope to not only detect extremely faint galaxies from the distant past, but also to provide insights into their histories and the processes that have shaped them. The ability to discern the reasons behind a galaxy's inactivity from such a vast distance is a testament to the power and precision of this observational tool. As we continue to explore the universe with the James Webb Space Telescope, more revelations about our galaxy and others are anticipated. For now, this wraps up our current discussion on the fascinating discoveries made by the James Webb. I invite you to check out previous videos for more insights into space and science. Share this knowledge with those keen on learning and return for more enlightening content. Your support through platforms like Patreon is always appreciated and helps in bringing more discoveries to light. The James Webb Space Telescope, with its unparalleled vision, has recently identified a collection of the most distant galaxies ever seen. These galaxies date back to within a few 100 million years of the Big Bang, offering us a glimpse into the universe's infancy. This discovery not only challenges our previous understanding, but also opens new doors for understanding galaxy formation and evolution. Delving deeper, James Webb has provided unprecedented details about the chemical composition and physical properties of these ancient galaxies. It revealed the presence of heavy elements and complex molecules, suggesting that star formation began earlier and was more rapid than previously thought. This insight is crucial for astronomers to piece together the puzzle how the universe transitioned from a state of simplicity to complexity. One of the most intriguing findings relates to the role of dark matter in the formation of these ancient galaxies. The James Webb's observations suggest that dark matter played a significant role in pulling together the gas and dust necessary for galaxy formation. This challenges earlier theories and provides a new perspective on the influence of dark matter in the cosmic structure. The James Webb has also shed light on the evolution of galaxies through time. By comparing these ancient galaxies with their more modern counterparts, astronomers can now trace the path of galactic growth and transformation. This comparative study is crucial for understanding the life cycle of galaxies and the various factors that influence their development. The discoveries made by the James Webb Space Telescope have far-reaching implications for future research. They not only refine our understanding of the universe's early days, but also set the stage for new questions and explorations. With each finding, we inch closer to unraveling the mysteries of the cosmos, making it an exciting time for astronomy and space science. The findings from the James Webb have profound implications for cosmology, the study of the universe's origin, structure, and eventual fate. By observing the earliest galaxies, we gain crucial data that can refine our models of the Big Bang and cosmic inflation. These ancient galaxies serve as beacons, illuminating the conditions of the early universe and helping us understand the initial distribution of matter and energy. One of the most groundbreaking revelations concerns the process of star formation in these ancient galaxies. The James Webb's data indicates that stars in these early galaxies formed at a much faster rate than previously believed. This rapid star formation, occurring under conditions vastly different from those in the Milky Way, challenges our understanding of stellar evolution and life cycle. Another intriguing discovery is the presence of supermassive black holes in some of the earliest galaxies. These findings pose the question of how such massive objects could have formed so quickly after the Big Bang. Studying these ancient black holes provides valuable insights into the relationship between galaxies and their central black holes, as well as the mechanisms driving their incredible growth. The James Webb has captured evidence of galactic mergers and interactions in the ancient universe, offering a new perspective on galaxy assembly and growth. These early mergers were crucial in shaping the size and structure of galaxies, highlighting the dynamic and often violent history of the cosmos. Understanding these processes is key to piecing together the evolutionary path of galaxies across billions of years. Cosmic dust in these ancient galaxies tells its own story, revealing information about the environments in which stars and planets form. The James Webb's observations suggest that dust production occurred at a rapid pace, contributing to the complexity of early galaxies. Studying this dust can provide clues about the formation of solar systems, including our own. James Webb's spectroscopic analysis has allowed scientists to trace the evolution of chemical elements across the universe's history. By examining the light from ancient galaxies, researchers can identify the signatures of various elements, offering insights into nuclear fusion processes in stars and the distribution of elements necessary for life as we know it. The intense cosmic radiation in the early universe had a significant impact on galaxy formation and evolution. The James Webb Telescope's findings are helping scientists understand how radiation influenced the cooling of gas clouds, star formation rates, and the ionization of the intergalactic medium. This research is critical for comprehending the mechanisms that shaped the early cosmos. Observations of galactic winds and feedback processes in ancient galaxies provide another piece of the puzzle. These phenomena, driven by star formation and supermassive black hole activity, play a crucial role in regulating galaxy growth. By studying these processes, astronomers can better understand how galaxies expel and recycle gas, influencing future star formation and evolution. The diversity in size, shape, and color of the ancient galaxies observed by the James Webb challenges the notion of a uniform, early universe. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.